Hello friends, in this video I'd like to solve the following problem from the Slovenian International Mathematical Olympiad Team Selection Test 2005, problem number 2. It's a functional equation. We wish to find all functions from the set of positive real numbers into itself such that x squared times f of x plus f of y equals x plus y times f of y times f of x for all positive numbers x and y. It's a nice problem. Here are my hints. First, try changing y to f of y, and then try showing that our function must be injective. And sadly, you have to do it by definition. So suppose that f of x equals f of y for some positive numbers x and y, and try to show that it means that x equals y. The fact that we are dealing with positive numbers will be useful. It's the hardest part of this problem. Once you show that our function is injective, set x and y to be 1 and find f of 1, and finally set x to be 1 and find f of y. So give this problem a try and I will see you in just a minute. Okay, so here is my solution. As I suggested, first let's change y to f of y in our condition, in our very first functional equation, asterisk. What do we have? We have x squared f of x plus f of y equals x plus f of y times f of y times f of x. I did it to produce symmetric expression in these parentheses. And now we'll show that our function is injective. So now suppose that f of x equals f of y for some real positive numbers x and y. Okay, notice the following. Or maybe before we do it, let's also, because we are dealing with positive numbers, we'll transform the previous equation a little bit, because it can be written that x squared over x plus f of y equals f of x times f of y over f of x plus f of y. Okay, and now we'll do the following. Notice that x squared over x plus f of y, it's the same, as we know, as f of x times f of y over f of x plus f of y. But also, I can change x and y. And I can write f of y times f of x over f of y plus f of x. Why can I do it? Well, because I'm supposing that f of x equals f of y. So I can freely change f of x to be f of y and vice versa. But then this is equal to y squared over y plus f of x. Perfect. And now we'll take these expressions written in green and we will multiply them, getting rid of the denominators. So that equals y squared x plus f of y. And now we can do the following. Let's put everything on one side. So we have x squared y minus xy squared plus x squared f of x. And finally, I will do one more thing. F of y, remember, it's exactly the same as f of x. So I can write minus y squared times f of x instead of f of y. and that equals 0. Very well, and now common factors. Here we have common factor of x minus y, and we have x times y. And here we have f of x plus y, f of x minus y, and that equals 0. Well, why is that? Because x minus y times x plus y is x squared minus y squared, and that's exactly what we have in the previous line. And we have yet another common factor, x minus y, xy plus x plus y times f of x equals 0. But now notice that our function takes only positive arguments and returns only positive values. So everything there is clearly a positive number. So for that equation to be true, there is only one possibility, namely x must be equal y. So we have now demonstrated that if f of x equals f of y, x must be equal y, i.e., let's write it, i.e. f must be injective. Very crucial. It's the most important part in this whole argument. Now, let's go back to our very first equation, and I will set x and y to be just 1. So I will have 1, f of 1, so 2 times f of 1, and here we'll have 2 f of 1. So 2f of 1 equals 2 times f of 1. So let's set x and y to be 1 in our very first condition asterisk. Then, as we have noticed, 2 times f of 1 equals 2 times f of 1. So f of 1 equals f of 1. And now, using injectivity, since here we have f of something, on the right hand side we have f of something else, by injectivity, which I will mark square, by our condition square, it must be the case that f of 1 actually equals 1. And finally, let's take just x to be 1 in our very first condition. Then let's take a look. What do we have? X is 1. So we have 1 times f of 1 plus f of y. So f of 1 plus f of y equals, and on the right hand side, what do we have? 1 plus y times f of y times f of 1. 1 plus y times f of y times f of 1. And I will use this condition, which I marked triangle. By our condition triangle, this is 1, this is 1 as well. So by condition triangle, 1 plus f of y equals 1 plus y times f of y. Perfect, because now we can multiply the right hand side and we'll get 1 equals 1 times f of y, which means that for every positive number y, f of y must be equal 1 over y. It's the only possibility. But now it's time to verify our result. Verification. So we will take the left hand side and the right hand side of our very first initial condition asterisk. On the left hand side, we have x squared f of x plus f of y. Sorry. So it's x squared 1 over x plus 1 over y equals x plus x squared over y. And on the right hand side, we have what exactly? We have x plus y, f of y times f of x, if I remember correctly. So x plus y plus 1 over y times 1 over x, x plus y, x over y. If we multiply, it's x squared over y plus x, exactly the same. So in fact, this function is the only solution of our equation. So yes, that's it. A very nice problem. A very, very nice functional equation. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.